Okay, today we're going to talk about classical field theory, and it's a big topic, so I'm going to break it up into two parts. Part A is Lagrangian mechanics and deriving the Lagrangian density, and part B will be on something called Noether's theorem to allow us to derive the Hamiltonian from the Hamiltonian density if we're given the Lagrangian density. Um, I'm not trying to make you an expert on all of classical mechanics and classical field theory. We are looking at quantum field theory as our main goal. And the real purpose of this is to try to learn the relevant classical field theory in a focused way that will allow us to derive the Hamiltonian of quantum field theory. Just to quickly recap on what we've done so far, we have clearly defined and created our Hilbert space in the previous lectures for quantum field theory, which we call the quote-unquote huge Hilbert space. Remember that this was done by taking the tensor product of the individual Hilbert spaces of each of the n to the third voxels that our space was broken into. Each individual voxel Hilbert space is obtained by considering the set of all possible values for a point moving along a one-dimensional track. We clearly defined quote-unquote promoted operators on our huge Hilbert space. These were things like phi of x1, x2, x3. There's a different phi at every point in space. And pi of x1, x2, x3, where x1, x2, and x3 are the x, y, z axes that just simply names which voxel we're talking about. There was a natural quantum mechanical way in which we can define phi and pi. They're really the x and p operators of this ball moving on the one-dimensional track. And by using the idea of tensor product, we can create a huge Hilbert space, and we could promote these operators to actually operate on the huge Hilbert space rather than just the individual Hilbert space that they originally came from. We also talked about another operator, the partial derivative operator, which you might want to call d phi, dxi, and xi could either be 1, 2, or 3. And these are technically different operators taken from different voxels anywhere along the point in space. And this also had a well-defined definition on our huge Hilbert space. So we've done our first big task of quantum mechanics, where we talked about in any quantum mechanical system, you really should first define your Hilbert space. That's the mathematical arena in which everything is going to take place. And also which operators are in play. And these are the three big operators, the phi, pi, and the partial derivative, d phi, dxi. The next big thing in any quantum mechanical system is now to talk about the Hamiltonian. Now, the Hamiltonian is just another operator. And if you remember, just like in ordinary quantum mechanics, we can use the phi and the pi operators to build other operators, which are a function of phi and pi, just the way we used x and p operators in regular quantum mechanics and build other operators out of x and p. Same thing. X and p or phi and pi are very well defined. So any operator which is built out of that will also be well defined. In particular, we're going to build, as I mentioned, the most important operator in quantum mechanics, and that's the Hamiltonian operator H. When you do regular quantum mechanics, sometimes we just kind of ad hoc pick, what H should be, or we use something inspired maybe by classical laws such as Coulomb's law. For example, when people solve the hydrogen atom in quantum mechanics, you may just kind of jump to things that you kind of already know, adjust it a little bit, depending on if you need to, based on some principle or sometimes even an experiment. But here, what we're really trying to do in quantum field theory is pretty dramatic. We are actually trying to find the underlying fundamental laws of the universe at the most basic level. And the idea is at the level of space that's created out of voxels and a one-dimensional ball moving up and down. So we might expect, therefore, rather than kind of ad hoc just throwing a Hamiltonian out there and seeing what we get, that we might, quote unquote, be able to derive the Hamiltonian from fundamental laws by appealing to the most beautiful principles. These things are somewhat subjective, but not so much either. What are the most beautiful principles? Well, symmetry. In this context, we specifically mean space-time symmetry, or Einstein's special theory of relativity. As far as we can always see, every law of physics obeys the special theory of relativity. There's a symmetry with respect to inertial frames that we see in all the fundamental laws of physics. The second one is locality, where things that are right next to each other can influence each other, but things that are not right next to each other cannot directly influence each other. And that's the idea of locality, and I'll tell you what that means. And the last one is, again, probably the most subjective. Dirac talked about this a lot, but it's the idea of mathematical simplicity, that we start with the most simple things. And for some reason, that seems to be the way physical laws are inspired, or at least follow. In these two lectures, we're actually going to backtrack. And even though our goal is quantum field theory and finding the Hamiltonian for our huge Hilbert space system of quantum field theory, we are going to backtrack and just only talk about classical physics. So we're going to take off our quantum field theory hat and our quantum mechanics hat and just talk about classical physics. And we're going to come up with ultimately, after two lectures, a Hamiltonian for a classical model of the ball going up and down a 1D track at every point in space. And we're going to just completely take that, rip that Hamiltonian that we derive for classical physics and use that later for quantum field theory. And it works out basically perfectly well. And it matches experiment perfectly well, as we'll eventually get to. And the ideas we're going to use are these three. And we're going to apply them in this case just to classical fields for a while. So take off your quantum hats and your quantum field theory hats and just think of now as a classical field. So what's the classical field? Well, let's just say you have a three-dimensional space, and at every point in space, you have a real number. I think you could still think of it as that ball moving on the 1D track at every point in space. And now it's not a superposition of states, it's just a number. And that's a classical field, a number at every point in space. I'm going to first start talking about Lagrangian mechanics, and this may not be familiar to everybody. I really had to self-learn virtually all of physics myself, so I haven't taken a lot of quote-unquote formal classes. I'm going to try to explain the relevant parts of Lagrangian mechanics here. It, of course, will help if you have some background or maybe even read further, but at least let me try to get the big points across that you really need to know in a focused way. We're going to get to quantum fields in a moment and real scalar, sorry, I apologize. We're going to get to scalar fields in a moment and real scalar fields, not quantum fields. But even before we do that, let's just review having a system with a very low number of degrees of freedom, basically just a particle moving in space, not a set of field values at every point in space, but just a particle. Suppose we have a system of one particle, which occupies at any given time t a certain position x. Remember now, just forget quantum mechanics, we're just thinking classically. Classical mechanics says that any physical system can be described by a function called its Lagrangian L, where this Lagrangian is some function of the position of the particle at a given time, and its first derivative, dx dt at that time, and maybe some more derivatives. It turns out for everything we're going to do, we're just only going to go with first derivatives. And this will tie into the idea of locality later. Suppose this is, everyone in physics from high school may remember as F equal ma and other things. There's a different way of describing physics, which is actually more powerful, which is what we're explaining now, called the Lagrangian formalism. And that's what everything high-level physics is really based on. Suppose at time t naught, our particle is at position x of t naught. So right now at t naught, it's in one particular position, x of t naught. And that at a later time, tf, the particle position is x of tf. We ask the question, what is the exact path in space that the particle courses between in time t0 to time tf? So you start at one point in space at t0, another point in space at tf, and you just want to ask the question, where does the particle go in between those two? What kind of path does it follow? So here's x of t naught, x of tf. Does it follow this path? Does it follow this path? Does it follow this path? What kind of path does it follow? Is there a way in physics that we can answer this question? Well, let's start by considering one particular path. Here's the answer in physics according to Lagrangian mechanics. If you look at this path at any given time, along the path, the particle has a particular value for the two following values. So like, let's say at this particular point in time, here's where the particle is. It started off here, ends up here, and we find some time in between, and here's our particle right over here. This particular position has a particular x value. This, when I have x with a arrow above it, it's a three-dimensional vector, so it's really x, y, and z coordinate, or x1, x2, and x3 coordinate. And if you just took the next snapshot in time, it's going to be somewhere else, and you can figure out what the derivative of the particle is with respect to time here. It's velocity vector, dx dt right over here. So at this given particular point in time, this particle has a x position vector and a velocity vector, dx dt. Therefore, at exactly this time, there's an exact value for the Lagrangian. So at this particular time, L of t, the Lagrangian is going to be, and we'll talk about which functions, but it's going to be some sort of function where you input what the x is and you input what the velocity is, the dx dt, and it spits out, according to your formula for the Lagrangian, what L is. So it spits out a real number over here. If we break up our entire path into infinitesimally small time pieces, dt, we can calculate the following quantity called the action. So you can break up every little part of this into this particle moving along this track. And at every given point, there's an x, there's a dx dt. And you can calculate this following value, the integral, where you break up the thing into all these different paths, and then you sum at each particular point or each particular time what L is at that time, multiplied by dt. And then you just jump to the next point, figure out what L is at that time, and what dt, and multiply it by dt, and then you add everything together, and that's what we mean by the integral. This quantity is called the action, the integral of L dt. In this case, we've calculated the action just for this particular path, which you might want to just call path 1, between times TO and TF, but when it follows this specific path. So there's an action, which is this whole integral to this particular path. We need to know the formula for the Lagrangian, but assuming it has a given formula, when you pick a path, you plug that x and dx dt into that path at each point, you integrate it, and you get an action for that particular path. Different path, obviously, will have a different action. So this is the action for path 2. You integrate now over this path and over L dt, Lagrangian times dt. Path 3 obviously has a different action as well. So you saw 3 different paths, they have 3 different actions, and then obviously you have an infinite number of different paths, each of which has its own particular action. Here's the big statement. Classical mechanics states that this is actually the law of physics that nature follows. So it kind of backs up, instead of saying it follows Newton's laws 1, 2, and 3, it instead looks at physics from a very different perspective, which is actually a more powerful and still consistent way with Newtonian mechanics of looking at it. And it states the following: that the actual path followed by any particle in the universe will be the path which has the smallest possible value for the action S. So we just talked about 3 different paths, each of which has its own different action. You can look at every conceivable path between these 2 points, and the path that this particle will actually follow between x and x of tf is going to be that which has the lowest possible action. If you find any path that has a lower action, then that's the one that it's going to be. And if there's one any lower, it'll take that one. It'll actually do the specific one that has the lowest possible action. This becomes an interesting math problem that people, I guess a couple, 200, 300, 400 years ago looked at and solved. And there's a wonderful branch of physics called calculus of variations, and you can solve the problem. I won't teach that now. There's some relatively simple ways and relatively short ways of seeing the derivation. But according to the calculus of variations, this problem has its solution the following: d dt, the time derivative of this quantity, the partial derivative of the Lagrangian with respect to the velocity vector, is equal to minus dl dxi. This famous equation, which was solved by Euler and Lagrange, is called the Euler-Lagrange equation. And it's true for if I is equal to the x-axis, or 1, if I is equal to the y-axis, or 2, or if I is equal to the z-axis, which is 3. So it's kind of 3 separate equations, one for each axis. Here's the equation written above again, and I'll show you an example of how we use this equation in a very general example for physics. Suppose we have a particle in a conservative force field, and just kind of going back again for people that may not be that familiar with this. According to multivariable calculus, a conservative force field has the following. It means that the curl of the force field is equal to 0. So you have this vector field, which is a vector at every point in space. This is a 2-dimensional example, but it could be 3 dimensions. And the curl of that is equal to 0. that means that this vector field is curl-free, and we call the field that's associated with that vector conservative if this statement is followed. If you have a curl-free vector field, or a conservative force field in this case, then if you have any 2 points in space, A and B, and you calculate this quantity, f dot dr, so if you have a path from here to here, and along that path, you break it up into little segments, and each segment has a directed line segment called dr, and at each segment where you're talking about along that particular path, there's a value for the vector field there. And if you do f dot dr, the dot product, and you integrate that quantity over the entire path, that quantity is path independent. These are results from a multivariable calculus, which hopefully you've taken. And if we pick some reference point, x naught, like somewhere here, we just pick some point to be our reference point, we can calculate at any other point in space x this number. So if this is our reference point here, with respect to this reference point, let's say we want to know this number, f dot dr, from here to here, we could pick any path, since the final integral is path independent in a conservative force field, and calculate that quantity in an unambiguous way. So what that gives us is a new value with respect to this point, of which is just the real number at any point in space. And that's called the potential, or the potential energy. And that's usually symbolized by V or U. In this case, I use V of X. So that we just have another real scalar field called V of X. All this is the potential. Many people may kind of laugh and say, obviously I know what the potential is. I'm used to that from quantum mechanics, but that's actually what it is. And according to everything, we can also just say the following statement, which is true just based on this in multivariable calculus, that at any given point in space, if we have this new real scalar field called the potential field, if we take its gradient, the gradient of the field V, minus that, we can reproduce our original force field. So F equals minus the gradient of V. We now can reformulate our physical problem and say that our particle, instead of it saying it's moving in a conservative force field, we can just say it's moving in a potential field V of X. And this may be familiar to a lot of people, but just to make sure that we understand what it means to say that our particle is moving in a potential field, we may initially think of things intuitively as forces, but once we get past that and move up in physics, we'll say that it's moving in a potential field V of X. That's a classic statement. We have a particle moving in a potential field V of X. Now, here's the physical law that we say. We've been pretty general. We just say we have a particle in space and it's living in space. It has a position. That's a very generalized statement. And this space itself has some sort of potential associated with it at every point in space, V of X. What physical law does nature follow in this situation? This is the physical law that's postulated. That the physical law that's postulated is that the Lagrangian of this system that we talked about, of a single particle in a potential, is as follows: 1/2 the mass of the particle times its velocity squared, the derivative of the xi component squared, and there's actually a sum here, minus, it's the sum of x1, x2, and x3, minus v of x. So you may remember this as t minus v for those of you who are familiar with Lagrangian mechanics. And by xi, as I said here, it's equal to the x1 squared plus the time derivative of x1 squared plus time derivative of x2 squared plus the time derivative of x3 squared. Okay, just looking at this formula here. Now let's plug that Lagrangian into our Euler-Lagrange equation right over here and see what we get. The way this is, it looks more complicated than it actually is you first need to calculate this quantity. Well, at least that's what we're going to calculate first, dl dx dot. And what this means is we just look at this expression and we think of x dot as just its own variable, nothing even related to x. Just think of x dot as if it's, another letter y. So we want to know what the partial derivative of L is with respect to x dot. So all we do is we take the partial derivative of this, thinking of x dot as a different variable than x. And if we do that, we just look at this term. This term will have a zero partial derivative with respect to x dot, because v is only a function of x. And we'll take the partial derivative of this when we get 2 times 1/2 times m times x dot. And that the 2's cancel, and we just get mx dot. So that's what this partial derivative is. If we then just plug that whole thing into the Euler-Lagrange equation, here's what we get. The left side is just d dt of what we just figured out here, mx dot. So d dt of mx dot is this. And then the right side is just the partial derivative with respect to xi of this part. So dl dxi, there's no xi here, there's only an x dot. So you think of that as different. And then this partial derivative dl dxi will just be of this, which is just kind of rewriting dv dxi. And there's a minus sign there. And if we equate the two according to the Euler-Lagrange equation, this is what we get. But the left side is d dt of m x I dot, assuming that m is invariant in time. We just get m times double x dot I is equal to this. But if you remember, f equals minus the gradient of v, which is this formula over here. So this whole thing is really nothing but f. So we have Newton's famous equation, F equals ma. So this Lagrangian formalism, which is a more powerful way of stating the laws of physics, does reproduce Newton's law of F equals ma. So this just kind of shows you that this is consistent with what our intuitive initial feel for F equals ma that we learned. So we've reproduced Newton's laws, which we know in classical physics correctly describes nature. Just stating things before, which is still worth hearing. In higher level physics, instead of starting with the assumption that F equals ma, etc., it's more advantageous to start with the previous principle, which is called the principle of least action for obvious reasons. It's sometimes, if you look at the calculus of variation or any basic derivation, symbolized like this, that this delta of s equals 0, meaning that you pick the path that has the lowest action. Technically, you can't say it's the lowest. It's something like the second derivative in calculus tells you that there's an extremum there, but how do you know it's the minimum, not the maximum? But we'll think of it as the minimum, but technically we're just calculating the extremum. As a recap, we first postulated a Lagrangian L for our physical system. You take a guess as to what it is in that previous situation, and it came out to be that T minus V kind of formula that you saw previously for a single particle. We use the principle of least action to give us our, quote, local marching orders, or our differential equations of our particle. Mathematically, this is obtained from the Euler-Lagrange equation. So that's Lagrangian mechanics for a single particle. The same idea can apply to an entire scalar field. We're again not getting into quantum anything right now, but we're talking about now we're going to extend, instead of just saying we have one particle that can move anywhere in space, we are now going to have a million particles, one at each point in space, that can only move along a 1D track. That's also called a scalar field. Suppose at every point in space, at any given time, we now have a field, which is really just at any given point in space, at any given time, you just have a real number assigned to it. Remember the notation we used, which is common in quantum field theory, that we often just write x with no arrow on it, and that is short for three spatial dimensions, x1, x2, x3, and one time dimension. We just usually write it psi of x. When there's no arrow, it just means 4 dimensions. Right now, again, we're not doing quantum mechanics or quantum field theory, so phi x is just the real number, not an operator. In classical field theory, we want to ask the same question: how does phi of x evolve in time? So just like we want to know how the particle evolves in time, we want to know how phi of x evolves in time. We do the exact same kind of formula. According to quantum mechanics and classical field theory, we do this by first defining a Lagrangian L for our system. L of t will be the spatial integral of a more fundamental quantity called the Lagrangian density, and it's an L written in calligraphy. We'll use this so often that sometimes by accident or even in real textbooks on purpose, you're going to just call this the Lagrangian, but technically this L, calligraphic L, is the Lagrangian density, which applies for classical field theory. So what does that mean? Well, this. Well, at any given time t in our whole system, even though now we have multiple degrees of freedom at every point in space, we still have this L of t, like we did for single particle physics, but that's just defined as the integral over space of the Lagrangian density, all at the same time. So we have a Lagrangian density at every point, we integrate over all space, and we get an L of t. According to classical field theory and classical mechanics, the system will evolve in such a way that this action, which is the same action that we talked about before, which is just the integral over time of L taken at any given time dt, is at a minimum, or really more accurately called stationary, at an extremum. So the same exact idea, that we calculate at any given time are Lagrangian, which will come from Lagrangian density, and then integrate that over time, and then we get an action for that particular path. What is a path? Well, let me show you here. Suppose at a time t0, our system is in configuration phi of x t naught. So like we're at some initial starting time, and at every point in space, we have a single value, a single real number of phi. That's at t0. Then let's say we go to some future time tf, and we have an exact configuration specified then. And now we ask the question, between times t0 and tf, what does the system do? How does phi change at every given point in space, at any given point in time between those two? What does physics tell us about that? Well, that's the question we're trying to answer. If we want to know exactly how our system behaves in between time t0 and tf, meaning what is the value of the scalar field at every intermediate point in time, we must choose a quote-unquote path. A path, by definition, is you tell me one specific set of values between t0 and tf that the scalar field will occupy at every given point in space, at every given point in time between those two times. The values of the field phi at all intermediate times between t0 and tf, such that this action is at a minimum. So it's the same exact principle that for any given path, we start at t0, we have a specific value of phi at every given point in space. We end at tf, we have a fixed value of phi at every given point in space. Between those two, we try every possible path. And associated with any particular path, which in this case is a field value specified everywhere in space between those two times, we can calculate a Lagrangian, and then we integrate that with respect to time, and then we get an action for that path. According to classical field theory and Lagrangian mechanics, the system will still obey the principle that what path it actually will take of all the conceivable paths will be that in which the action is at a minimum or an extremum. Here you just see that we're integrating over time of the Lagrangian, but the Lagrangian itself in classical field theory can be broken up into a Lagrangian density at every given point in space, and then you integrate that over space to get the full L. That's the calligraphic L again, and then the regular L over here. So roughly, you give me a path, a phi of x, let's say, constrained by that at t0, it's one specific set of field values, and at tf, it's another specific set of field values, but you give me some path between it. I have a formula, which we'll get to, called the Lagrangian density, which is going to be inputting phi and its derivatives, which we'll get to in a moment. But once I have that formula postulated, I go from a phi for a given path, and I get a Lagrangian density at every point. If I integrate the Lagrangian density at every point, at one specific, at every point at any given time, then I can get a Lagrangian at that particular time. I'm just integrating over space here. And then once I know the Lagrangian at any given point in time, or at every given point in time, then I can just calculate the action with this way. So any given path will ultimately give me a given action. And if I look to see which path has the least ultimate action, that'll be the path that the thing actually follows. This explains the same thing. Now, does math help us? It does again. Luckily, some very smart mathematicians, Euler, Lagrange, solved this very interesting calculus type problem. I think it goes under the name of calculus of variations, the way I kind of learned it, was self-taught. And just like we had an Euler-Lagrange equation for a single particle, we have the same exact, very analogous type of thing for a classical field. And this is the formula. The partial derivative with respect to mu of this quantity, which is the partial derivative of the Lagrangian density, with respect to the partial derivative of the partial derivative with respect to mu of phi, minus this, the partial derivative of the Lagrangian density with respect to phi, equals 0, the Euler-Lagrange equation. We'll go over some more specifics of this in the next slide. Again, it looks more complicated than it usually is once you start to work with it. The Lagrangian density itself is a function of phi. And you tell me what phi is at any given point, and its first derivatives, which is d phi dt with respect to time, and its first derivative with respect to space. And in this case, the space part's new because we didn't have that first singular particle. And then I can get a Lagrangian density. In our course here, we just have first derivatives, and I'll explain a little bit why. That has to do with principle of locality. And the same reason for time has to do with symmetry, which we'll get to in a little bit in the near future here. And this is called the Euler-Lagrange equation for fields. This begs the question, what is L for the scalar field? We said we're going to postulate a certain type of Lagrangian density for our field. Once we do that, we can plug different possible fields into our system, see which has the lowest action, and that will be the path that the field actually follows. Or we can use Euler-Lagrange equation. But either way, we need to know what is the Lagrangian density for a given configuration, for a given field, and its first derivatives. Remember that Lagrangian density is a direct function of phi and its spatial and time derivatives, its first derivatives. And this is where we come up with what I mentioned before. According to the principle of locality, we can only use first derivatives for this expression. Now, why is that? Well, if you think about things, or you can go back to basic calculus, first year calculus, single variable calculus, there's something called the Taylor expansion of any function. And basically, as long as we're using first derivatives, that means that only immediately neighboring points can influence each other. To calculate the first derivative, let's say you broke space up into lots of different points. If you want to figure out the first derivative of a function, you really just have to know what the immediate next value in space. If you look at one specific point in space, you have to know the next immediately adjacent value in space to come up with the first derivative. To come up with second derivatives, you have to start looking at the second point in space, the second nearest neighbor, not the nearest neighbor. And that would actually violate the principle of locality if we started using second derivatives. What about time? Why do we only use the first derivative with respect to time? Well, we know from special relativity that there will always be a symmetry between space and time. They're really intertwined. And for reasons of consistency, the formulas will actually bear this out, we can only use, it would kind of violate special relativity if we had a first derivative only in space and a second derivative in time. So that's why we're also restricted to use first derivatives of space and first derivatives of time. So this is why we say our Lagrangian density will just be some sort of function of phi itself and the first derivatives of phi with respect to space and the first derivatives of phi with respect to time. I love special relativity, and we can talk about this for a while, and I may or may not do a full lecture on that. We'll probably get to things later, but for now, we're going to assume some familiarity with special relativity and really highlight the biggest points that we need to keep moving forward in our focus study of quantum field theory. David Tong, I love his lecture note, Development of Quantum Field Theory, is a good source for a lot of what I'm talking about. I have stuff explained in some different ways than him, and I think the principle is built up by a lot of his lecture notes. I like the way he develops quantum field theory, especially at the initial level or the first pass level, I'll say that. And he has some nice discussions on special relativity, which at some point are worth going over, but I'll try to go over some more of this right now. And he also has some great stuff on classical field theory and Lagrangian mechanics as well in his quantum field theory early parts of his notes. The big point of special relativity is that we can achieve that the laws of physics are Lorentz invariant, meaning that if we change one frame of reference to another frame of reference moving at a constant velocity with respect to that first one, the laws of physics should be such that they're identical. Nature does not make different laws of physics depending on your frame of reference. As long as they're, with respect to each other, inertial, the laws of physics in those inertial frame of references are identical. And the beautiful geometric idea in special relativity, assuming that we've taken it all, is that you can actually achieve this by looking at quote-unquote four-dimensional geometric objects that exist not only in space, but in space-time. And these objects, if you stick with them in your formulation of your laws of physics, you will have automatic Lorentz invariance. It's as if nature lives in 4 dimensions when it thinks of laws of physics, even though we think of it as space and time. And if you stick with 4D geometric objects and use that as your principle, I'm only going to create laws of physics that use 4D geometric objects, I'll automatically have Lorentz invariance. That's really a way of stating the principle of special relativity. What are the classic 4D geometric objects that are used in special relativity? Well, there's Lorentz scalars, a real value defined at every point in space at any given time that is assumed to be exactly the same if you change your space-time coordinates, which is really the same as you change your frame of reference from one inertial frame to another. Lorentz four vectors, and there's covariant and contravariant four vectors. Again, I'm not going to review this. I'm assuming that you have familiarity with special relativity. And there's other things that are just as you go up in number of the depth of your mathematical objects, you go from scalars to vectors to tensors, or four tensors that are defined in space-time. We're not going to get into too much of four tensors. I'll mention it a little bit, but these are our basic geometric objects that we're going to use here. And then you can use some of these objects and do certain operations that are also Lorentz invariant, namely a contraction. We'll contract four vectors, in particular covariant and contravariant ones, to produce a Lorentz invariant scalar. These are standard things in special relativity. I don't want to get too off tangent, so I just kind of use these to help inspire where we come up with our laws that are going to be relevant for quantum field theory. So let's just start simple. Let's assume we have a field defined at every point in space at a given point in time. It's just a real number at every given point. If we coordinatize our physical field, then phi of x will be expressed differently elsewhere, but the actual value at any given space-time point is constant. Let's just assume. So the phi of x is a Lorentz scalar when we talk about any real physical field. So that's an automatic. Phi of x squared is obviously also a Lorentz scalar. Let's just define another Lorentz scalar called m, which is the same value at every given point in space at a given point in time. That's called the mass of our object that's being described in the field, which for now is just a number, or let's just say it's a positive number, so we can call it m squared. Then obviously if we do 1/2, which is a Lorentz scalar, times m squared, which is a Lorentz scalar, times phi squared, which is a Lorentz scalar, the whole thing is a Lorentz scalar. If phi is a Lorentz scalar, then according to basic special relativity, the partial derivative d mu phi is a Lorentz covariant four vector. We can take any scalar field, Lorentz scalar field, and form its du, its d mu, partial derivative, and we will get a quantity that's a four vector, that's a true Lorentz covariant four vector that transforms in the correct way. Again, basic special relativity. We can raise this in the standard way in special relativity, where we use the metric, which we defined on one of the previous lectures, as basically the first 1 or the 0 part of it is 1, and then all the other ones are negative. The time part is 1, and the other parts are -1 on the diagonal, and everything else is 0. It's this, I think it's called eta mu v. I self-taught physics, so some of these things I may mispronounce because I don't have the advantage of a lot of stuff I read was in books. But this is how you can raise a vector. If you have a covariant vector and you raise it, you can get this, and this is our symbol, that d with mu raised is this. And that's a Lorentz contravariant four vector. And this is, I did have this here. This is what our definition is for our space-time metric. This we'll use throughout the entire course here. Most quantum field theory books use this. Unfortunately, some reverse it and use the other formulation, but this is what we're going to use here. And we could form a Lorentz covariant scalar by contracting a covariant with a contravariant four vector. So if you take this covariant four vector and its contravariant four vector, if you contract them, where repeated indices are sum, this is the Einstein summation convention, familiar hopefully with everybody that took special relativity at the appropriate level. We just get a single number, because this is going to be 0, 0, plus 1, 1, plus 2, 2, plus 3, 3, and the whole thing, if you add it, it's just a single number, and that single number will end up being another Lorentz scalar. So this gives us our Lorentz scalar. So very simple, nothing complicated, as long as you know it, a little bit familiarity with special relativity. If we just do what we just did, the following proposed Lagrangian density will satisfy special relativity and locality. I added a factor of 1/2, but this is very simple. I just say that the Lagrangian density at any given space-time point is equal to 1/2 times this value, which is a covariant four vector derived by taking d mu of phi, multiplied by its contravariant part, subtracted from this Lorentz scalar. This whole thing will be a Lorentz scalar, and this will be a Lorentz scalar, just the phi field itself. Very simple. I'm not getting into more complicated things. That hopefully kind of satisfies the idea of simplicity. The 1/2 will help me out here. Potentially you don't have to, have a whole theory to arrive with the 1/2, but the 1/2 makes things a lot easier mathematically later, and we have some arbitrariness being able to throw that in there. But this is about as simple as it can be. We hope that nature will actually satisfy something simple. This is a relationship that we're going to assume is a law of physics for our free scalar field, and it turns out it's correct. It's as simple as possible. You have just first derivatives and very simple special relativity Lorentz invariant geometric objects that just gives us a final scalar for the Lagrangian density at a given point. So this is our formula. If you expand this out to just have some more familiarity breaking up space and time indices, you get this. Sometimes when you expand this out, you have to somehow either implicitly say that di means that, or you have to put the sum over I. Just that's all this means, nothing complicated. So this kind of summarizes the same thing. We took a 4-vector, another 4-vector, contracted them to get a scalar. Here we had a scalar, another scalar, and we subtract one scalar from another, and the whole thing is the Lagrangian density, which itself is a nice Lorentz invariant scalar. Very simply constructed, and we only use first derivatives with respect to space and time, obeying this principle of locality. Now we have our Lagrangian density for our scalar field, which is our key object right now. It's our key object in quantum field theory. We're right now just not doing anything quantum, just classical. But that classical field is really a key object, our scalar field. It's like the one ball on the 1D track moving up and down at every single point in space, at every single voxel. And now we have our Lagrangian density. Now we can solve our problem. How does this thing change in time? If I have a phi at any given point in time and a phi at a different point in time, exactly what path, meaning what value will the scalar field take between those 2 points in time at every given point in space? That's our path. Well, we just use a Lagrangian density, and this will actually give us our differential equation, or our quote-unquote local marching orders that phi will have to obey. And here it is here. I'm just going to take this thing and plug it into here. And I'll show you an example of how this equation is used, and why it's not necessarily quite as hard as you think. There's some tedious things you have to keep track of when you're doing it, and we'll show you hopefully step by step. And let's see what we get. If we plug this thing into here, let's see what equation of motion we get for phi. So the first thing is we're plugging this into here. We got to first figure out this term over here. So what is it? I'm going to just jump to a different slide, but our goal right now is just to calculate this part. We'll come back to this part, which is easier in a moment, but I'm going to jump to a different slide that just shows us calculating this part over here. What is that? Let's just break our Lagrangian density up into L1 and L2, and this is the part that we're going to try to focus on right now in our Lagrangian density, the part that has the partial derivatives. If we just expand this out to know exactly what it means, there's an Einstein summation convention here, so we have to put 0, 0, 1, 1, 2, 2, 3, 3, which is just symbolized by I, and this is itself a summation, Einstein summation convention over this. Whenever we use a Greek or Latin, I guess this is called, index, the index by tradition will run 0 to 3, so there'll be 4 things, 0, 1, 2, and 3. Whenever we just use a, I guess, English, or I think it's called Roman, but whatever, like a regular standard alphabet letter like I or J or K, that by definition only runs from 1 to 3, 1, 2, and 3. So we expand that out, that's what we get. This part will come up over and over again, so it's important to be clear in quantum field theory. If I want to drop this downstairs instead of upstairs, I can just use my metric to do that. Given the metric that we're using, that we talked about before, every time I go from an upstairs D0 to a downstairs D0, I don't have to do anything. I can just drop it downstairs without changing any sign. So that's this expression rewritten here is D0 stays here. This upstairs D0 goes straight down. In contrast, whenever I do the spatial parts, the 1, 2, and 3, the I's, whenever I drop that down, I have to put a negative sign. And that's explained right over here. If I have a 4-vector like this, if I want to drop it to its covariant or downstairs part, I keep this the same and I put a minus sign in front of these other components. So this thing becomes minus. So now I've just expressed this part of my Lagrangian, which is the part I need to calculate that first part that I showed in the previous slide, like this. You can write this as follows. This is d0 phi quantity squared minus di phi quantity squared. And if I write it like that, now I can just crank out my part of my formula that I needed for the Euler-Lagrange equation, which I rewrote over here based on this. Flip back to the previous slide, is this. This is the thing I wanted to calculate. And if I just do this, how do I interpret this? Well, first thing, I just want to expand this out again before I even look at this. And this is another Einstein summation convention where I just go 0, 0, and I, and I is 1, 2, 3, if there's a summation here. And that's all I get. And now I can focus on looking at this part and this part by looking at this expansion that I have that makes it a little bit easier. And this is where things are somewhat easier than you think. If I just want to do this, the Lagrangian partial derivative with respect to that, I just think of this entire quantity, d0 phi, as just one single variable, like x or y or whatever you want to call it. And this whole thing is one particular quantity, and I just take the partial derivative with respect to that. And here's what I get. 2 pulls out over here, and I just get this with its first derivative, so d0 phi. This part over here is going to be this, the same thing with the minus sign, minus di d phi. So the final thing I'm going to get for this part of the Lagrangian is this expression here, this thing, minus this thing. I just plugged that back into over here, and now I have this original d naught. This d naught is this d naught, and this part over here is this part over here, so that's why I get a d naught of d naught phi, minus the same thing here. I have this original di, and then this part over here is this over here. So I get 2 di's in a row and 2 d naughts in a row, minus, and then just to be clear, I put a summation over I. Sometimes I'll put it, sometimes we won't. Most quantum field theory books start getting rid of that just because it makes for messy, but usually when you see the repeated indices, they should be summed, even if one's not upstairs and one's not downstairs, which some old special relativity books that I first read said only matters if it's up or down. But in this case, if it's repeated, it's usually going to be summed unless you say it's not summed. That's pretty classic for quantum field theory books. All right, so anyway, that's the expression I have over here. Going back to our original thing, back to the slide, remember our goal was to first calculate this part, and we just did that on the previous slide. So I'll get rid of the question mark and tell you that's what we just figured out. So this part over here is this. What's this part? This part's a little bit easier. Now just look right back over here, and now we just do the partial derivative of this with respect to this. These two guys are considered not this, so they don't apply to this term. So all we're doing when we do the partial derivative here is over here. This part would be 0 with respect to this partial derivative. So we just do the partial derivative of this thing with respect to phi. I'll do that in a second. Before that, I just want to express one more thing with notation. I apologize going back. If I see something like this, d0, d0 phi, I can just write that as d0 squared. That just implies that I take the second derivative. So I take the first derivative with respect to time and the derivative of that with respect to time, which is nothing but the second derivative. And we usually write that as this thing squared, kind of like an operator squared, d0 squared. It's this. And this thing over here is usually written as di squared. And that summation, when I do it like this, is implied as well for this particular notation. Even more notation stuff, which is still important, it just allows us to express things more elegantly and start getting rid of a lot of sum signs and everything else, is this notation. You'll see this a lot in Anthony Z's book. It's also a very good book once you know what you're talking about. Is this squared? I think they call this the del squared. And by definition, whenever you see this, I guess, del squared sign, it means this. It means that it's an operator that I just write d0 squared, the second derivative of time squared, minus this sum, which is sometimes written like this, di squared. And then this phi should not be there. Sorry, it should not be there. Now, getting back to this guy over here, the partial derivative of that term, very easy. We can just look right at it and do the partial derivative of this with respect to just phi. This part would be 0. I just pull out the 2, and I get, m squared phi. This 2 drops down this way, 2 times a half, m squared, and I get m squared phi. There's a minus sign here, which we'll now get to, and now all I have to do is I know this part, minus, and I know this part, and I'm just going to combine the two together and get this. This is a very important formula in quantum field theory. Right now, we're just not even doing anything quantum. So technically, this formula applies even though we're not even doing anything quantum in classical physics. And this is called a Klein coordinate equation. And using these standard notational things, this is it, very simply expressed. This is the actual equation that this scalar field is going to follow. It's the simplest equation that obeys special relativity, locality, maybe ideas of simplicity and beauty that you can possibly create. And it turns out it's the equation that nature will follow as well. We're going to get to more complicated things that actually describe more common things in nature, like electrons and photons, but that is a little bit more complicated to deal with. And I want to focus on the big points of quantum field theory using the scalar field, which will really teach us a lot of very important things in quantum field theory. And the rest are going to be not that hard to extrapolate once we've done the free scalar field, which is all we're doing now. So the Klein-Gordon equation is right here. So just to summarize, our big goal, remember, is to find the Hamiltonian for quantum field theory. We just took a big detour, and we're still going to continue the detour when we get to part 2 next. But in order to do this, we first needed to use classical mechanics and classical field theory, CFT, coupled with some compelling arguments of using symmetry, locality, and simplicity to derive H for a classical theory of a scalar field. We reviewed classical mechanics and classical field theory in this lecture. Our big result is that any classical field gets its local marching orders, or the differential equation that it must obey is this, called the Euler-Lagrange equation. And we showed a good example of working with that. It's not as complicated as you think, just sometimes a little tedious. You have to be careful with signs and things like that, and raising and lowering things. We then focused on saying, all right, this is the equation that our classical field will follow, but what is the Lagrangian formula itself? What is the postulate of our physical system for Lagrangian density? And instead of just ad hoc assuming what the form of this function is going to be, we again use these 3 compelling arguments of symmetry, locality, and simplicity, and we derive this very simple and somewhat beautiful, I'd argue, formula for the Lagrangian density. When we just take that formula for Lagrangian density and we throw it into the Euler-Lagrange equation, we get this also very simple and beautiful formula called the Klein-Gordon equation, which is as follows.